All right, we're moving into our magnetism unit, or part of the electromagnetism unit. We're going to talk about magnetism. And so I'm going to go over these notes with you today. First thing I want to point out, it says a magnetic domain is a region within a magnetic material in which the magnetization is in a uniform direction. This means the individual magnetic components of the atom are aligned with one another and they point in the same direction. So over here, when we look at a magnetic material, this is one way where you can draw it. Just draw arrows pointing in the same direction. They can be pointing horizontal, vertical, as long as they're going in the same direction. In a non-magnetic material, they're all in random places. So up, down, diagonal, to the side. They're all going different directions. So this is magnetized, this is not. I'm going to flip back and forth from the notes so you can see some stuff. Feel free to pause when you're drawing your things so that you can catch back up. All right, the next one says draw magnetic field lines if I have iron filings. So if I go over here and look at this, this is the iron filings that you should look at. Okay, my magnetism is going to be the strongest at the poles. These are my field lines. So when you draw it, it needs to look like this, where you're just sketching what the lines look like if there were iron filings coming off of it. The next thing we're going to move into is we're going to look at how a compass behaves around a bar magnet, and then I'm going to show you how to draw it. So in this SPET simulation, there's a link. If you want to do it, you can go and try it. It's showing you how all of these little magnets out here are the magnetic field. And so as I move the magnet around, the field changes. Okay, and the highlighted areas, it's strongest, and it's going to be strongest at the poles. So what's going to happen when I move this compass, which has a needle, the red end is north, the white end is south. If I move it around the bar magnet. Now, if I'm here, notice opposites attract, so the red needle will point towards the south. Okay, north is pointing to the south. If I move it up, because it's closer to the south, the opposites are going to attract. Okay, if I move it to the middle, it's going to be almost in the middle, where the red needle, which is north, is pointing to the opposite pole. The white needle, which is south, is pointing to the opposite pole. And then as I move it around, opposite south is attracted to the north. Okay, and so every place I move it in this is going to be attracted to the opposite pole. Now the link's there if you want to go and play with it. You can. Some of you don't have access to it unless you have Java on your computer, but this will help you as long as you've seen that. So what I want to do is I want to go back to my notes, and we're going to draw it on here. So what we had, I'm going to add in 2 extra spots. Okay, the north was pointing to the south was pointing to the north. Here, my north was here, my south was here, my south was here, my north was here. Okay, now I'm going to go around and see kind of how it was. North, south. Okay, and then you can see where the N is north and the S is south. Now on the next thing, it says click to see the inside of a magnet. Add your arrows to your drawing above to represent the magnet. So if we go back here and we click to see the inside, these are just like the domains that we saw earlier. Notice they're all pointing in the same direction. My north is on this end, my south is on this end. Okay, they're all going horizontally. They could all be going vertically, that's fine, but they're all going in the same direction. You don't have a north on one end and a south on the other. So because this is really dark right here, I'm going to draw an extra box. And I'm just going to do this, south, north, just so you can see what the domains would look like. As long as you understand that they are all aligned, you're fine. Okay. Next thing I want you to do is it says to draw the magnetic field lines. Make sure you draw arrows to represent the direction of the magnetic field. If I pull and look at this slide, This is what you should be drawing. Notice the arrows are coming out of the north and coming into the south. So you need to draw that and make sure they're coming out of the north. Now I know on your notes it's horizontal and this is vertical. That's fine. Make sure that they're coming out from the north and into the south. Going back to number 5, it says predict what would happen inside the magnet if the magnet were to break in half. So if I break a magnet in half, am I going to end up with 2 south poles and 2 north poles? Or am I going to end up with a south and a north and another south and north? And think to yourself, this is what the answer is. I end up with 2 new magnets. So if I'm looking at the second row, both with their own north and south pole. If I continue to break them down, they each continue to have a new north and south pole. And so that's what you should be drawing or sketching in there. All right. The next thing I want you to look at number 6. It says draw the magnetic field lines around each pair of magnets. Now we know from elementary school that like poles are going to repel and opposite poles are going to attract. And so that looks like this. So like poles are attracting and opposites are repelling. Make sure that you copy them in the same direction on your paper, okay? So I think your paper is reversed from this. Make sure that you get them done, okay? Then we move on to our next piece of information. And our next piece of information is talking about inducing magnetism. Now, we can make magnetism happen by simply taking a magnetic, like iron or a nail, and stroking and making everything go in, all the domains go in one direction. So it says some non-magnetic metals can be magnetized through induction. And if you refer back to the video that we watched over magnetism from GPTV, it shows this happening, okay? In order for induced magnetism to happen, the domains of the magnet must be all in one direction. So this would show it all in one direction. These are all varied. This is magnetized, this is not. All right, and then the last thing you should have, if you read the article on electromagnetism, you should know a wire carrying a current produces a magnetic field. Okay, and then we go back to this next simulation. So the last few questions are using that simulation. All right, I'm going to click electromagnet. And here, I've got an electric current pushing through this, and it's producing a magnetic field. If I move this around, notice the field moves with it. So the field's going to be strongest at the bottom because that's where the electricity is forming. But notice there is a field at the top. And so what I'm going to do is I'm going to move the compass around, and I want you to see what it's doing. Is the compass moving? Yes, the compass is moving. It's attracted to opposite poles, proving that there is magnetism going through this electric current. Okay, so number 10 says explain how the behavior of the compass near the bar magnet and electromagnet are similar. You need to write in that they are attracted, the compass is attracted to opposite poles in both. The compass is attracted to opposite poles in both. All right, next one. It says, notice the moving blue dots in the wire are moving electrons. So these things right here are electrons. What is going to happen to these blue dots if I make the voltage 0? So ask yourself that. All right, let's see. Make my voltage 0. Are the electrons moving? No. So for A, what happens to the motion? When it's 0, they stop. B says, move the compass around the battery and the wire. Does the compass move? Well, first thing we need to notice is there's no field around here. So do you think the compass is going to move? If there's no electricity, there's no magnetism. So notice the compass doesn't move. So the answer to B was no. Is there a magnetic field around the system? For C, the answer is also no. Now, I'm going to change it from AC to DC, and I want you to see what happens. DC was all in one direction, AC is going to alternate. Okay, so what do you notice? What's the compass doing? The compass is flipping poles, so every time the current changes, it flips the poles of the magnet, which makes the compass change. So that's what you need to write for 12. The poles are reversing every time the current changes. All right, so if you have any questions, make sure you are asking.